Hello. Hi, it's everyone. No one comes to my streams, so I'm basically learning on my own. Anyways, so wait, hold on. Let me just change to full screen. Uh, okay, so last stream we completed chapter 2. We learned about functions and scopes and header files and so on. This time we'll start with chapter 3. It talks about errors and debugging. I barely use debugging. I use a lot of print statements when going through my program. I think this chapter would be useful for me. Anyways, so starting with 3.1, syntax error. Programming can be challenging, and C++ is somewhat of a cookie language. Put those two together, and there you have two ways. There you have a lot of ways to make mistake. Errors generally fall into one of two categories: syntax errors and semantic errors. Semantic errors are logic errors. A syntax error occurs when you write a statement that is not valid according to the grammar of the C++ language. This includes errors such as missing semicolons, mismatched parentheses, or braces. For example, the following program contains quite a few syntax errors. Uh, Extraneous semicolon, variable names can't start with a number, missing closing bracket. Yeah. A semantic error is an error in meaning. These occur when a statement is syntactically valid but either violates other rules of the language or does not do what the programmer intended. Some kind of semantic errors can be caught by the compiler. Common examples include using an undeclared variable, type mismatch, etc. For example, the following program contains several compile time semantic errors. X not declared cannot assign a value to 5. Hello cannot be converted to an int. Other semantic errors only manifest at runtime. Sometimes these will cause your program to crash, such as in the case of division by 0. But we haven't done arithmetic, right? I don't think so. More often, these will just produce the wrong value or behavior. So over here, int x, they're printing x and it's uninitialized. This won't produce an error. It will just output the garbage value. And x minus y. There's a wrong operator being used. Should produce 8 but produces 2. Function returns here, so this never executes. Okay, this was a small chapter. 3.2, the debugging process. Because we haven't covered that many C++ topics yet, our example programs in this chapter is going to be very basic. That may make some of the technique we are showing here seem excessive. However, keep in mind that these techniques are designed to be used with larger, more complex programs. A general approach to debugging. Once a program has been identified, debugging the problem generally consists of 6 steps. Finding the root cause of the problem, ensure you understand why the issue is occurring, determine how you'll fix the issue, repair the issue causing the problem, retest to ensure the problem has been fixed, retest to ensure no new problems have emerged. Find the root cause. Since you're here, okay, let's say one evening you go to get some ice from the ice dispenser in your freezer. You put your cup to the dispenser, press the lever, and nothing comes out. You have discovered some kind of defect. What do? Find the root cause. Since you hear the ice dispenser trying to deliver ice, it's probably not the ice delivery mechanism itself. Oh, since you hear the ice dispenser trying to deliver ice, it's probably not the ice delivery mechanism itself. So you open the freezer and try to examine the ice tray. No ice. Is that the root cause of the issue? No, it's another symptom. After further examination, you determine that the ice maker does not appear to be making ice. Is the problem the ice maker or something else? The freezer is still cold, the water line isn't clogged, and everything else seems to be working. So you conclude the root cause is that the ice maker is non-functional. Understand the problem. This is simple in this case. Determine a fix. At this point, you have several options for a fix. You could work around the issue, buy bags of ice. You could try to diagnose the ice maker further to see if there's a part that can be repaired. You could buy a new ice maker and install it in place of the current one. Repair the issue and retest. Now let's apply this process to a sample program from the previous lesson. This code is nice in one regard. The bug is very apparent because the wrong answer gets printed to the screen via line 10. Okay, it should show 8, but it shows 2. Find the root cause. On line 10, we can see that we are passing in literals for arguments 5 and 8, so there is no room for error there. Since the inputs to the function add are correct, but the output isn't, it's pretty apparent that function add must be producing the wrong value. The only statement in function add is the return statement, which must be the culprit. We have found the problem line. Understand the problem. In this case, it's obvious why the wrong value is being generated. We are using the wrong operator. Determine a fix. We are simply changing the operator minus to plus. Repair the issue. What's the difference between these two steps? Then lastly, retest. Determine how you will fix the issue, repair the issue. Okay, this is planning how to fix the issue, and this is actually fixing the issue, I think. These chapters are really small. I think in this stream I would have to do both 3 and 4. We will see. When debugging a program, in most cases, the vast majority of your time will be spent trying to find where the error actually is. Once the issue is found, the remaining steps are often trivial in comparison. Finding problems via code inspection. Consider the following code snippet: get names, sort names, print names. If you expected this program to print the names in alphabetical order, but it printed them in opposite order instead, the problem is probably in the sort names function. In cases where you can narrow the problem down to a specific function, you may be able to spot the issue just by looking at the code. Okay. However, as programs get more complex, finding issues by code inspection becomes more complex as well. First, there's a lot more code to look at. Looking at every line of code in a program that is thousands of lines long can take a really long time. Second, the code itself tends to be more complex with more possible places for things to go wrong. Third, the code's behavior may not give you many clues as to where things are going wrong. If you wrote a program to output stock recommendations and it actually output nothing at all, you probably wouldn't have much of a lead on where to start looking for the problem. Finally, bugs can be caused by making bad assumptions. It's almost impossible to visually spot a bug caused by a bad assumption because you're likely to make a bad assumption when inspecting the code and not notice the error. What do they mean by bad assumption? Finding problems by running the program. Fortunately, if you can't find the issue via code inspection, there's another avenue we can take. You can watch the behavior of the program as it runs and try to diagnose the issue from that. This approach can be generalized as figure out how to reproduce the problem, run the program and gather information to narrow down where the problem is, repeat the prior step until you find the problem. For the rest of this chapter, we will discuss techniques to facilitate this approach. Reproducing the problem. The first and most important step in finding a problem is to be able to reproduce the problem. Reproducing the problem means making the problem appear again in a consistent manner. If a software issue is blatant, then reproducing the problem can be trivial. However, sometimes reproducing an issue can be a lot more difficult. The problem may only occur on certain computers or in particular circumstances. In such cases, generating a set of reproduction steps can be helpful. Reproduction steps are a list of clear and precise steps that can be followed to cause an issue to recur with a high level of predictability. So homing in on issues. Once we can reasonably produce the problem, the next step is to figure out where in the code the problem is. Based on the nature of the problem, this may be easy or difficult. For the sake of example, let's say we don't have much of an idea where the problem actually is. How do we find it? An analogy will serve us well here. Let's play a game of high-low. I'm going to ask you to guess a number between 1 and 10 for each guess you make. I'll tell you whether each guess is too high, too low, or correct. 5 too low, 8 too high, 6 too low, then 7 correct. In the above game, you don't have to guess every number to find the number I was thinking of. We can use a similar process to debug programs. In the worst case, we may have no idea where the bug is. However, we do know the problem must be somewhere in the code that executes between beginning the program and the point where the program exhibits the first incorrect symptom that we can observe. That at least rules out parts of the program that executes after the first observable system. I see. In my previous stream, when I did the exercises, I don't think the stream captured it. I think the stream cut off at this point. So basically, last stream in the exercises, I was learning about the header files and these header guards. So I have this io.cpp which reads a number and then this right answer. Basically, the program reads a number and writes their sum. So read number is over here. Read your integer int x, and then store it in x, and then return it. Then main.cpp uses those functions. So read number once, read number second time, and then add them, store it in this variable, and then in the right answer function you output it to console. Okay, so if there's a bug, like if I get the wrong answer for some reason, if let's say there's a bug on this line. So what the text, what they're saying here is that we check if this part works. We check if somewhere in the code, like a random line, like let's say this, if we know this works, then we don't know that between this point and the end of the code, the bug exists somewhere in between. We have a really long code, like many lines, then if this line works, then we know from beginning to this line the program works properly. That's what they're saying here. Basic debugging tactics. Debugging tactic 1. Commenting out your code. Let's start with an easy one. If your program is exhibiting erroneous behavior, one way to reduce the amount of code you have is to search through. Is to comment some code out and see if the issue persists. Consider the following code. Let's say this program is supposed to print the names the user enters in alphabetical order, but it's printing them in reverse alphabetical order. Where's the problem? Is get names entering the names incorrectly? Uh, but we do suspect do maintenance has nothing to do with the problem. Let's comment it out. There are three likely outcomes. If the problem goes away, then do maintenance must be causing the problem. The problem is unchanged, then we can reasonably assume that do maintenance wasn't at fault. If commenting out do maintenance causes the problem to morph into some other related problem, then it's likely that do maintenance is doing something useful that some other code is dependent on. In this case, we probably can't tell whether the issue is do maintenance or elsewhere. So we uncomment do maintenance and try some other approach. Debugging tactic 2. Validating your code flow. Another problem common in more complex programs is that program is calling a function too many or too few times. In such cases, it can be helpful to place statements at the top of your function to print the function's name. That way, when the program runs, you can see each function getting called. When printing information for debugging purposes, use stdc error instead of stdc out. One reason for this is that stdc out may be buffered, which means a bit of time may pass between when you ask stdc out to output text and when it actually does. If you output using stdc out and then your program crashes immediately afterwards, stdc out may or may not have actually output yet. This can mislead you about where the issue is. On the other hand, stdc error is unbuffered. Is this correct C error? Which means anything you send it to it will output immediately. Using stdc error also helps make clear that the information being output is for an error rather than a normal case. Let's see. stdc error is an error. So if I do this, would it run main.cpp? It's no, it's still configuring, right? I mean, it's still compiling. Okay, let's see what this does. Enter an integer. Okay, this is an error. This is an error. So it does print, but I don't see. The only difference is that this is unbuffered, right? What's the difference between these two and these two? I think the debug for Visual Studio is different from the debugger here, what I'm guessing. You may need to disable treat warnings as error for the example above to compile. Although we expect this program to print the value 4, well, I don't expect it. It should print the value 1. On Visual Studio, it may print the following instead. Uh, let's add some debugging statements to these functions. So see error, get value called, see error, main called. Why is there no tab here? When adding a temporary debug statement, it can be helpful to not indent them. This makes them easier to find for removal later. Uh, Now when these functions execute, they will output their name indicating that they were called. Now we can see that function getValue was never called. Debugging tactic 3, printing values. With some type of bugs, the program may be calculating or passing the wrong value. We can also output the value of variables or expression to ensure that they are correct. Consider the following program that is supposed to add two numbers but doesn't work correctly. So print, let's see what the issue is. So main get user input, enter a number, right. So what the user types gets stored into X and Y. Then add works with X and 5, right. And then it gets stored in Z, and then Z gets printed. Here's some output. Okay, so the mistake is they put 5 and they're supposed to put Y. That's not right. Did you see the error? Even in the short program, it can be hard to spot. Right. See error X, see error Y, and see error Z. So when they find out that X and Y works correctly, but then Z doesn't, the problem would be somewhere in between here. So X is 4, Y is 5. Variable Y had value 3, but somehow our function add got the value 5 for parameter Y. We must have passed the wrong argument, sure enough. One more example. This program is very similar to the prior one, but also doesn't work like it should. Let's add X, Y, Z. What's the difference? Oh, yeah. Minus minus X. So they're adding a lot of print statements. They're trying to find where the. I think this print statement would be wrong. I think both x and y would be wrong. Yeah, 3 and 2. Uh, okay, they haven't covered the minus minus prefix. I'm assuming they will in the future chapter. Why using print statements to debug isn't great. And that's what I did in Python a lot. While adding debug statements to programs for diagnostic purposes is a common rudimentary technique and a functional one, it's not great for a number of reasons. Debug statements clutter your code. Debug statements clutter the output of your program. Debug statements require modification of your code to both add and to remove, which can introduce new bugs. Debug statements must be removed after you're done with them, which makes them non-reusable. We can do better. Some more debug tactics. So, okay. So we introduced why adding print statements everywhere is bad. Conditioning your, now let's read about conditioning your debugging code. When you're done with debugging statements, you will either need to remove, wait, remove the debug statements or comment them out. Then if you want them again later, you will have to add them back or uncomment them. One way to make it easier to disable and enable debugging throughout your program is to make your debugging statements conditional using preprocessor directives. So enable debug and put the debug in the if statements of the preprocessor directive. Now we can enable debugging simply by commenting or uncommenting define enable debug. This allows us to reuse added debug statements and then just disable them when we are done with them, rather than having to actually remove them from the code. Uh, the This addresses the issue with having to remove debug statements and the risk in doing so, but at the cost of even more code clutter. Another downside of this approach is that if you make a typo or forget to include the header into a code file, some or all of the debugging for that file may not be enabled. I think if you make a spelling mistake, it won't catch it right. It will just like not put this in the compiled version. An alternative approach to conditionalize debugging via the preprocessor is to send your debugging information to a log. A log is a sequential record of events that have happened, usually timestamped. This process of generating log is called logging. Typically, logs are written to a file on disk called a log file so they can be reviewed later. Most applications and operating systems write log files that can be used to help diagnose issues that occur. Log files have a few advantages because the information written to a log file is separated from your program's output. You can avoid the clutter caused by mingling your normal output and debug output. Log files can also be easily sent to other people for diagnosis. So if someone using your software has an issue, you can ask them to send the log file. It might help them give them a clue where the issue is. C++ contains an output stream named stdclog. that is intended to be used for writing logging information. However, by default, stdc log writes to standard error stream, the same as stdc error. And while you can redirect it to a file instead, this is one area where you are generally better off using one of the many existing third-party logging tools available. Uh, Blog is implemented as a set of header files and it's lightweight. So blog is it? It's third party, right? So debug main called, and then get user input. I forgot this is a PDF, so scrolling won't work. How you include, initialize, and use a logger will vary depending on the specific logger you select. Can't we make our own logger with uh, file manipulation? Note that conditional compilation directives are also not required using this method, as most loggers have a method to reduce eliminate writing output to the log. This makes the code a lot easier to read. If you want to compile the above example code yourself or use the plug in your project, you can follow these instructions to install it. Okay, I will maybe read that some other time if I want to. Okay, using an integrated debugger. When you run your program, execution begins at the top of the main file and then proceeds sequentially, statement by statement, until the program ends. At any point in time when your program is running, the program is keeping track of a lot of things. The value of the variables you're using, which functions have been called, uh, all of this is all of this tracked information is called your program state. Behind the techniques we have shown so far is an unstated assumption that once we run the code, it will run to completion, only pausing to accept input with no opportunity for us to intervene and inspect the results of the program at whatever point we want. However, what if we were able to remove this assumption? A debugger is a computer program that allows the programmer to control how another program executes and examine the program state while that program is running. For example, the program can use a debugger to execute a program line by line, examining the value of variables along the way. By comparing the actual value of variables to what is expected or watching the path of execution through the code, the debugger can help immensely in tracking down semantic logic errors. The remainder of this chapter will be spent learning how to use the debugger. You mean the entire chapter 3? Don't neglect learning to use a debugger. As your programs get more complicated, the amount of time you spend learning to use the integrated debugger effectively will pale in comparison to the amount of time you have finding and fixing issues. So now I need the debug version of this, which is much slower. If I run this, What happens? Nothing. Maybe local Windows debugger. Isn't there a thing where I can like read all the memory location of the variables? So I wanna read for VS. We are going to start our exploration of the debugger by first examining some of the debugging tools that allow us to control the way a program executes. Stepping is the name of a set of related debugger features that let us execute our code statement by statement. The step into command executes the next statement in a normal execution path of the program and then pauses execution of the program so we can examine the program state using the debugger. Let's debug this program using the step into command. First locate and then execute the step into debug command once. Yeah, this is what I was searching. So starting diagnostic tools. What are all these things it loaded? Or this is from the IO stream, right? Yeah, this is going to take a really long time. Thread has exited with code 0. Oh, it completes first. So what this is, this a debug and then step into. It is confusing to me. So int main, right? The arrow is here. And then what? Do I press continue? Because we did a step into, you should see some kind of marker appear to the left of the opening brace of function main. In Visual Studio, this marker is a yellow arrow. Okay, so that's the point of execution. Then I think we Wait, the arrow marker, and then choose step into to execute the opening brace, and the arrow will move to the next statement. What did it mean choose step into? Show next statement, step into, step over, step out. If I click continue, would it go through the entire thing? You know what this is? You have no clue what's happening. So read number and then enter your integer. Then, oh no, it's going to open stdc out. Can I do? What is step out? Why does this take so long? 500 milliseconds. This step over. 4 2000 milliseconds. Oh, that's because they were waiting for the input, right? Right answer. Oh no. Right answer. Skip this. The sum is 9. And then end. And goes back to normal view. Okay, choose step into yet again, which will execute the statement stdc out value. The version of the operator used for the output is implemented as a function. As a result, your IDE may step into the implementation of the operator. This is called the insertion operator, right? If this happens, you will see your IDE open a new code file, and the arrow marker will move to the top of the function named this. This is part of the standard library. Close the code file that just opened, then find and execute step out debug command. The instructions are below under the step out section. In the prior lesson, we mentioned that stdc out is buffered, which means there may be a delay between when you ask stdc out to print a value and when it actually does. Because of this, you may not see the value 5 appear at this point. To ensure that all the output from stdc out is output immediately, you can temporarily add the following statement at the top of your main function. Steady unit buff. Enable automatic flushing for stdc out. Or when this goes inside the buffer, then it will be flushed. Okay, we did all this. Note that stop debugging can be used at any point in the debugging process to end the debugging session. Congratulations, you have now stepped through a program and watched every line execute. Like step into the step over command executes the next statement in the normal execution path of the program. However, whereas step 2 will enter function calls and execute them line by line, step over will execute an entire function without stopping and return control to you after the function has been executed. I thought step out goes to the previous thing or the exit statement as well. Stop debugging. So enter your integer. Wait, hold on. We do step into, right, or F11. Unlike the other two stepping commands, step out does not just execute the next line of code. Instead, it executes all remaining code in the function currently being executed and then returns control to you when the function has returned. So wait, let me think. If I do step into debug, step into, so arrow is here, and then it goes to read number, and then it goes to this line. Now from here onwards, if I press step over, it goes to the next line, right? Goes from line 5 and jumps to line 7. Then step into, right, now if I do this again, if I do step out, right, it goes out of the entire function, read number function. Okay, so this skips a line, this goes out of the function. Guess that makes sense. Right answer. Oops. And up, step out. Now, whoops. Step out again. Skip line. And then it should print. Yeah. And then step out. Why does it go here? What is this? So stop debugging. A step too far. When stepping through a program, you can normally only step forward. It's very easy to accidentally step past the place you wanted to examine. If you step past your intended destination, the usual thing is to stop debugging, restart debugging again, being a little more careful to not step your target this time. Some debuggers, such as Windows Studio, okay, I don't have this, so let's just skip. 3.7. I think I'll just finish chapter 3 because it's like 4 a.m., almost 5 a.m. Run to cursor. The first useful command is commonly called run to cursor. This run to cursor command executes the program until execution reaches the statement selected by your cursor. Then it returns control to you so you can debug starting at that point. This makes an effective way to start debugging at a particular point in your code, or if already debugging it, to move straight to some place if you want to examine further. Run to cursor by right clicking a statement in your code and choosing run to cursor from the context menu. So let's see. Run to cursor. So it starts debugging, and the first time it reaches that line, it's gonna give control to me. Yeah. And what happened to my input? I already pressed 5 and enter, right? So that's why maybe it didn't. Okay, I get the point. Continue. Once you're in the middle of a debugging session, you may want to just run the program from that point forward. The easiest way to do is to use the continue command. The debug command simply continues running the program as per normal, either until the program terminates. Okay, let's see. So if I do start debugging from here, oh yeah, this continue button I was asking. Four, then go next, and then just continue from this point onwards as a normal function, like without debugging. Yeah. Start, the continue command has a twin brother named start. Start command performs the same action as continue, just starting from the beginning of the program. It can only be invoked when you're not already in a debug session. Start command performs the same action as continue, just starting from the beginning of the program. Breakpoints. The last topic we are going to talk about in this section is breakpoint. A breakpoint is a special marker that tells the debugger to stop execution of the program at a breakpoint when running in debug mode. Toggle break, choosing breakpoint from the context menu. I think we can do breakpoint. This line does the breakpoint, right? So we can do this. So what happens? Choose the start command to have the debugger run your code, and let's see the breakpoint in action. You will notice that instead of running all the way to the end of the program, the debugger stops at that breakpoint. So I have a breakpoint. Let's put it here. Now run the debugger. Start debugging. I thought I did it at int 6. And if I put a remove this debugger and put it here, and then I press continue, it reaches the next breakpoint. Right. Then I can step over and then end the debugging. Yeah, that actually makes sense. I think I should change the color of these. Instead of white, I think white or gray, I think dark blue, like the color of these line numbers. And maybe I should change the color of the arrow as well. Breakpoints have a couple of advantages over run to cursor. First, a breakpoint will cause a debugger to return control to you every time they're encountered. Okay. There's one more debugging command that's used fairly uncommonly. I thought the breakpoint was the last thing they would talk about, but is at least worth knowing about, even if you won't use it very often. The set next statement command allows us to change the point of execution to some other statement, sometimes informally called jumping. This can be used to jump the point of execution forwards and skip some code that would otherwise execute. Uh, you can jump the point of execution by right clicking on a statement, choosing set next statement from the context menu. Let's see. Set next. Set next statement from the context menu. It's not here. Control Shift F10. I think I have to start debugging, then it will do next. Hold on. Let's see. Debugging, start debugging. Let's see. Can I do it now? Nope, I can't. Let's see jumping forwards in action. First, run to cursor on line to line 11. At this point, you will see the value 5 in the console output. Print value 5. Next, click on line 12. Choose next set next statement. This will cause line 11 to be skipped and not execute. Hold on. Where is it though? Okay, so let's say I do um run to cursor here. So it does this, and then so where's set next statement? Is it show next statement? No, set next statement. Ah, it's here. Set next statement. What is show next statement? Okay, and then set next statement to a different function. Are you sure? Yes. Int x. What gets printed? The sum is minus. Oh, this is a garbage value. Step back rewinds the state of everything as if you've never gone past that point. Uh, this is essentially an undo command for stepping. Set next statement, when used to jump backwards, only changes the point of execution. Any changes to variable values or other program state are not undone. Okay, what's the next chapter? Watching variables. Let me just do this. I don't know how long that's gonna load. Using an integrated debugger. Watching a variable is the process of inspecting the value of a variable while the program is executing in debug mode. Most debuggers provide several ways to do this. Let's take a look at a sample program. This is a pretty straightforward sample program. It prints the numbers 1, 3, and 6. First, run to cursor to line 6. At this point, variable x has already been created and initialized with the value 1. So when we examine the value of x, we should expect to see value 1. The easiest way to examine the value of a simple variable like x is to hover your mouse over the variable. Okay, let's see. Can I copy and paste the code? So let's do int y this. Whoops, not this. And then int c. Why does it do that? Why does it cover the whole thing? Uh, y c. Now should do this. Let's see. Oh yeah, and include IO stream. So they should run properly. Just print 1, 3, and 4. So you can hover on X and see the value 1. Okay, let me see. Yeah, 1, 3, and 4. Now let's try it with, let's do step into. Step X is 1. Okay, so it's initialized to 0. So X is 0. And then step again. It gets assigned a 1. And then let's just step over. So 0, wait. No. Y is 0. Why does this have a value? Then step over, step over. Z is 514. Then it becomes 4. Then it gets outputted. Then we can stop the debugger there. So hovering works. Let's see. If you're using Visual Studio, you can also use Quick Watch. Highlight the variable name X with your mouse and then choose Quick Watch from the right click menu. What does Quick Watch do? This will pull up the sub window containing the current value of the variable and with the value. I think what we observed was the watch window. Like the window over here. I think it was the watch window, right? This is watch 1. What is autos? think autos, so local, then autos. Okay. Now I can add them manually. Right. Pull up on the watch window in the code window. The watch window can evaluate expressions too. The watch window will also allow you to evaluate simple expressions. If you haven't already, run to cursor to line 12, line to stdc out. Then try entering x plus 2 into the watch window and see what happens. It should evaluate to 8. You can also highlight an expression in your code, then expect the value of that expression via hovering or by adding it to the watch window. Local watches, by inspecting the value of local variables inside a function, is common while debugging. So I think this here, the local here is for the local variables. Alright. So what is autos? It just automatically adds the variables as it sees them. So what's this one about? So next is the call stack. Let me just pause this. Why isn't it opening? So the call stack is a list of all active functions that have been called to get to the current point of execution. The call stack includes an entry of each function call as well as which line of code will be returned to when the function returns. Whenever a new function is called, that function is added to the top of the call stack. When the current function returns to the caller, it is removed from the top of the call stack and control returns to the function just below it. The call stack window is a debugger window that shows the current call stack. If you don't see the call stack window, you will need to tell the IDE to show it. In Visual Studio's debug menu, Windows call stack. So let's go to a previous thing. Uh, debug debug menu, Windows call stack. Windows, where's the call stack? Let's take a look at a call stack using a sample program. Put a breakpoint on lines 5 and 10 of this program and start Then start debugging mode. Because function A is called first, the break line on line 5 will hit first. Okay, will be hit first. At this point, you should see something like this. Okay, let's see debug Windows. Debug Windows call stack. Okay, can I put like the call stack here? So main executes. Yeah, here right now, and then step next. Line 4, read number. Okay. Learning basics.exe. There's an exclamation mark, then read number, line 4. And then line 5. Oh, as soon as it executes, it goes here. I see. So read number, line 7. What just happened? Read number, line 8. And then it goes to main, line 4. Oh, and then it goes out of the stack. I see. Okay, I think I get it. Breakpoints. There are no breakpoints here. How do I, this window should be more like here. Yeah, I think it's better like this. Uh, close. Right. Close. Close. Okay, now let's see what they are. Other than the call stack, what else were they talking about? think this is the call stack. So main and then A, right? Main, then A. And then if they continue, A will go out of the call stack and then B enters in because it's a stack. Uh, let's see what the next lesson is about. Finding issues before they become problems. When you make a semantic error, that error may or may not be immediately noticeable when you run your program. An issue may lurk undetected in your code for a long time before newly introduced code or changed circumstances cause it to manifest as a program malfunction. Don't make errors. Well, the best thing is to not make errors in the first place. Here's a list of things that can help avoid making errors. Follow best practices. Don't program when tired or frustrated. Understand where common pitfalls are in a language. Don't let your functions get too long. Prefer using standard library to writing your own code. Comment your code liberally. Start with simple solutions. Avoid clever, non-obvious solution. Optimize for readability, maintainability, and not performance. So, refactoring your code. As you add new capabilities to your programs, you will find that some of your functions grow in length. As functions get longer, they get more complex and harder to understand. One way to address this is to break a single long function into multiple shorter functions. This process of making structural changes to your code without changing its behavior is called refactoring. The goal of refactoring is to make your program less complex by increasing its organization and modularity. What do they mean by modularity? So how long is too long for a function? Function that takes up one vertical screen worth of code is generally regarded as too long. If you have to scroll to read the whole function, the function's comprehensibility drops significantly. Ideally, a function should be less than 10 lines. Functions that are less than 5 lines are even better. Remember, the goal here is to maximize comprehension and maintainability. An introduction to defensive programming. Errors uh, can be not only of your own making, but also occur when your users use the application in a way that you did not anticipate. For example, if you ask the user to enter an integer and they enter a letter instead, how does your program behave in such a case? Defensive programming is a practice whereby programmers try to anticipate all of the ways the software could be misused, either by end users or by other developers. We will explore topics related to error handling in future lessons. Finding errors fast. Since not making errors is difficult in large programs, the next best thing is to catch errors you do make quickly. What? Since not making errors is difficult in large programs, the next best thing is to catch errors you do make quickly. Oh, I see. An introduction to testing functions. One common way to help uncover issues with your program is to write testing functions to exercise the code you have written. Here's a primitive attempt, more for illustrative purposes than anything. So add the test add function tests the add function by calling it with different values. If all the values match our expectations, then we can be reasonably confident the function works. Even better, we can keep this function around and run it anytime we change function add to ensure we haven't accidentally broken it. This is a primitive form of unit testing, which is a software testing method by which small units of source code are tested to determine whether they are correct. As with logging frameworks, there are many third party unit testing frameworks that can be used. An introduction to constraints. Constraints based technique involve the addition of some extra code to check that some set of assumptions or expectation are not violated. For example, if we were writing a function to calculate the factorial of a number which expects a non-negative argument, the function could check to make sure the caller passed in a non-negative number before proceeding. If the caller passes in a negative number, then the function could immediately error out rather than punching some indeterminate result, helping ensure the problem is caught immediately. Shortcutting for general issues. Programmers tend to make certain kind of common mistakes, and some of those mistakes can be discovered by programs trained to look for them. These programs, generally known as static analysis tools, sometimes informally called linters, are programs that analyze your source code to identify specific semantic issues. In this context, static means that these tools analyze the source code without executing it. The issues found by static analysis tools may or may not be the cause of any particular problems you're having. You already have one static analysis tool at your disposal, your compiler. Okay. Best practice, use a static analysis tool on your program to help find areas where your code is non compliant with best practices. Right. Let's just read the summary and quiz, and then I will end the stream there. So, a syntax error is an error that generally occurs when you write a statement that is not valid according to the grammar of the C++ language. The compiler will catch these errors. A semantic error occurs when a statement is syntactically valid but does not do what the programmer intended. The process of finding and removing errors from a program is called debugging. So, debugging, find the root cause, understand the problem, determine a fix, repair the issue, retest. Static analysis tools are tools that analyze your code and look for semantic issues that may indicate problems with your code. Okay, quiz time. The following program is supposed to add two numbers but doesn't work correctly. Use the integrated debugger to step through this program or what's the value of x. Let's see if I can find it manually. So x read number, so please enter a number, and then this over here x plus read number, then right answer sum is okay. Let's see what the issue is. First, let's normally run it. So one or more multiply defined symbols found. What's the issue? I mean, I'm not including them, right? Why would that be a problem? Okay, let's just do. Let's see. Enter a number 5, 4. The sum is 4. Let's see what they do. Actually, I could do this. Take this. Put it here. That's the normal way of doing it. Anyways, x read number. So let's see where the issue is. Let's do step into. What happened? Oh, whoops. Read number int. Now let's see. Okay. So next, int x value 468. That would be overwritten. So cn, I will put 5. Then x has the value 5. Now going. Read number return 5. Why does it say x has 0? So read number x as 0. Wait. So read number 5. Oh, 5. 5 gets returned, but it doesn't get assigned to this x. So that's the issue. So stop the debugging. Get rid of this line. And then start debugging. Five. Whoops. Read number x. I think what the user intended was this. So x goes in here, which is 0, and then it returns the input value. In my case, it was 5, and now then 5 gets assigned. And then next time, if it returns 4, then it becomes 5 plus 4. Let's like normally run it. Five, 4, 9. Now it's doing it correctly. The major issue is in the second line of the function main. The return value of read number isn't assigned to anything, so it is discarded. Minor issues that read number is taking an argument when it should have a local variable instead. So this is the right way. I mean, it assigns during the initialization. Question 2. What is the following program? The following program is supposed to divide two numbers but doesn't work correctly. Use integrated debugger to step through this program. For inputs, enter 8 and 4. So let's see. So it reads 8 and then it reads, oh, it's not assigned to y, it's assigned to x. The issue here is that the second call to read number accidentally assigns its value to x instead of y. Question 3. What does the call stack look like in the following program when the point of execution is on line 4? Only the function names are needed for this exercise, not the line numbers indicating the point of return. So main goes into stack, and then A goes into stack, then B goes into stack, and C goes into stack, but then it comes out of the stack, and then D goes into stack. So main A, B, D. Right. The following program is supposed to add two numbers but doesn't work correctly. This is extra credit. So X, Y, read X. Oh, character. It's not the right type. The issue is the char data type on line 6. When we enter a numeric value, it is not stored as the value 8, but it is stored as 56 instead. We haven't learned about char, so you're not supposed to know the detail. It's hard to find good examples of simple programs that are not obvious issues to debug, that have non-obvious issues to debug, given the limited material covered so far. Okay, I will end the stream here then. Finish chapter 3. And guess I will see you guys next time.